Welcome friends and welcome to my series of video lectures on design of steel structures. The topic of this video lecture is design of a bolted connection for lap joint. The expected outcome from this video is design a bolted connection for a lap joint. We are going to use some keywords in this key terms in this lecture. They are like this: single bolted and double bolted lap joint, bolt value, shear capacity of bolt, bearing capacity of bolt, bearing capacity of plate, working load, ultimate or factored load, bolt line or bolt row. Friends, we will understand the design of a bolted connection for lap joint through a numerical problem. The statement of the problem is as follows. Read the statement carefully and try to understand while reading. Design a lap joint to connect two plates of size 100 mm by 16 mm thick and 18 mm by 12 mm thick to transmit a tensile working load of 70 kN. Assume 4.6 grade bolts and plates of grade Fe 410. Now we will try to convert this problem into a diagram. Let us read the problem again. We will understand the problem by analyzing the statement of the problem, that there are two plates 100 mm by 16 mm and 80 mm by 12 mm thick. The thickness is mentioned as 16 mm and 12 mm. The other dimension is 100 mm by 80 mm. So let us look here. This is plate 1 and this is plate 2. We see that this is the top view. So lap joint means the one plate is put over the other, above the other. So we see here that the plate 2 is placed over the plate 1 because this line is appearing as dotted. So it means that it is below the plate 1. Now we see that the distance or the width of the plate is 80 mm for plate 2 and 100 mm for plate 1. Now if we look at the sectional view, we will see the thickness. In the top view we will see the width of the plate. In the sectional view we will see the thicknesses. We see here that the 100 mm wide plate is 16 mm thick and the 18 mm wide plate, that is plate 2, is 12 mm thick. Here we see the center line of the plate. So this is all about the arrangement of the plates. Now we want to connect these two plates by bolts. So we will be putting bolts here, here, here and so on. So we will be putting the bolts on this overlap distance. Now how many bolts we will require, what diameter of bolts, all that will be covered as a part of design. After having drawn the diagram clearly, we will now try to understand and interpret the data of the problem. We have to always remember that the statement of the problem, if it is understood perfectly, if we think on it perfectly, that means if you try to understand each and every word of that statement of the problem, the solution becomes obvious and it follows automatically. So let us look here, problem understanding and data interpretation. Let us read the problem again. In the problem we see that a working load of 70 kilonewton is given. Tensile working load. Here we can see these yellow arrows as the arrows acting outwards. These are the force arrows. These are the tensile forces or tensile loads. So since it is tension, the arrow tips are away from each other. So these are the, in the sectional view also we see the same. So in the top view also we see the same. Now here we have to understand between two important key terms, that is working load and ultimate load. We have decided earlier that we will be solving the problems of design of steel structures using limit state method. One of the important characteristics of limit state method is that it takes into calculation not the working loads but the ultimate or factored loads by applying the working load by a load factor. So we will first of all see here that in the problem they have given working load of 70 kilonewton. And we now have, right now we have said that we will convert that working load into ultimate or factored load. So the first interpretation of data is we will have to convert the working load T equal to 70 kilonewton given load into ultimate or factored load TU. U stands for ultimate, capital T stands for tensile load. So this is 1.5 into T. This 1.5 is the partial safety factor for load or the load factor 1.5. So this is 1.5 into 70, 105. So you will see in this diagram, we have not shown the load as 70 kilonewton as it was directly given. We have shown the load as 105 kilonewton, which is the ultimate load to be taken for calculations. Second interpretation of this statement is that the bolt grade is 4.6. Here it is given, assume 4.6 grade bolts. What is the meaning of this? As we have seen earlier in earlier videos, that the bolts are having some grades, they are graded. So the meaning of the bolt grade is this. If this is 4.6, this 4 into 100 gives the FUB or ultimate bolt stress. What is ultimate bolt stress? The bolt is made up of some material. So the material of the bolt is having ultimate stress value as FUB. This B stands for bolt, U stands for ultimate, FUB is the ultimate bolt stress. It is to be taken as, if this is 4, it is to be taken as 4 into 100, that is 400 Newton per mm square. So this is the meaning of 4. Then the meaning of 0.6 is here. The second value indicates the bolt yield stress, that is FYB. That is equal to 0.6 into 400, that is 240 Newton per mm square. Now what is this 4.6, 0.6 into 400? This 0.6 has come from this 4.6. So 0.6 has come here. So this is how we have to interpret the meaning of the bolt grade 4.6. The third thing is plates are of grade Fe410. What is the meaning of this? It means that the plate of steel of grade 410 is used. So in this it means Fu for the plate is 410 Newton per mm square. When it is Fu, it means that of the plate. When it is FUB, it means that of the bolt. So B stands for bolt, otherwise it is about the plate. So this is the interpretation of the data. Now we will proceed for the design procedure of this problem. So after having done this preliminary work, we will go for calculations of design. So we will go with step 1. Before we go for step 1, we will take some further data, further interpretation. We will assume a bolt of diameter 16 mm. The bolt diameter is not mentioned. What we are going to do is we are going to place 1, 2, 3, some correct number of bolts here. So when we are providing a bolt, the bolt must have some diameter. Now what is the diameter of the bolt? That is not mentioned in the problem statement. If it was mentioned in the problem statement, there was no question of assuming. But here that is not mentioned. So we have to assume bolt diameter D, small d, equal to 16 mm. Now we are assuming it as 16 mm. Now for a bolt diameter of 16 mm, we get all these numerical details. Whenever we are using a 16 mm bolt, we are using net bolt area. We know that a bolt is having two cross-sectional areas. One is the area at the shank, which is the gross area AG, and the area at the bottom at the root of the thread, which is 0.78 times Ag, which is called as net bolt area. All this we have taken already considered in the earlier video. This is just a revision of that. So we get for this 16 mm bolt A and B net bolt area equal to pi by 4 into 16 square into 0.78. 16 is the diameter of the bolt. So we get 156.78 mm square as net bolt area. Then the second, we have seen that whenever we want to use a bolt, we will have to make a bolt hole here. Okay, so that bolt hole will allow the bolt to pass. So the diameter of the bolt hole DH is D plus 2, that is 16 plus 2 mm, that is 18 mm. We have seen in earlier video that the bolt hole diameter DH is D plus something. That something depends on what is the value of D. So if we are having 16 mm bolt, we get that value as 2. So it is DH equal to D plus 2. So this is equal to 18 mm. You can refer to the earlier video for the other details of the bolt hole diameter. Then the next thing is, if we place some 1, 2, 3 bolts, what will be the distance between the two bolts? Every two bolts. So that distance will be called as pitch P, which we take usually as 2.5 D. So we are assuming pitch of the bolt as 2.5 D, that is 2.5 into 16, that is equal to 40 mm. Then we have to provide some edge distance. So edge distance is the distance of the last bolt center from the edge of the connection. So this we are taking as 1.5 DH. This is 1.5 into DH. DH means the bolt hole diameter, that is 18 mm. So this amounts to 27 mm. Now this 27 mm is a numerical answer, but on the site, on the construction site, it is difficult to provide an odd figure of 27 mm. So instead of that, we will round it off to 30 mm. So in the design, we have to take care that all the final dimensions which we provide, they are to be rounded off from practical point of view. Now this edge distance E is 1.5 DH. We had already seen that the value of edge distance E can have two values. 1.5 DH if the edges of the connection are sharp. Okay, they are smooth and sharp. If they are not sharp, they are rough. In that case, this instead of 1.5, you have to take it as 1.7 DH, as we have seen in the earlier video. But here we are assuming that the edges are sharp and smooth, and that is why we are taking this as 1.5 DH. So that was about edge distance. Now about this factor KB, we will look at it a little later. Now with this much of the basic data about the 16 mm bolt, 16 mm diameter bolt, we proceed for step 1 of the solution. Now we are supposed to design a bolted connection for this particular lap joint for a tensile load of 105 kilonewton. Now what is the exact meaning of designing a bolt connection? In simple words, to design a bolt connection means to decide the number of bolts which you are going to provide in this connection, and to decide the arrangement of the bolts. These are the two things we have to decide. So let us go for step 1. The first step, we have assumed bolt diameter at 16 mm, right? Now how many bolts of 16 mm will be required to transfer a force of 105 kilonewton? That is the core question. How many bolts will you require? 2, 3, 4. How many? For transfer of force of 105 kilonewton. How to decide this? Very obviously, to decide this, we should know how much force a single bolt will resist. If you take a single bolt, then how much force will it resist? That we will have to calculate first. Then we can decide accordingly how many bolts we will require to resist 105 kilonewton force. So we come across here a new term, that is bolt value. What is the meaning of the term bolt value? Bolt value is the value of of the of the force that a single bolt will resist. Bolt value is the value of force a single bolt will resist. Now, how to calculate this value? How do we know how to find out how much force a single bolt will resist? So that means what is the bolt value of 16 mm bolt? So for that, the IS 800 2007 has provided us a small rule. What is that rule? Bolt value BV is given by the value least means smallest of VDSB and VDPB. So we have to remember this rule very clearly. Bolt value BV is the least of VDSB and VDPB. Now, while we are going into the numerical calculations, we have to be careful about the symbols and their meanings. In every design problem, we have to handle so many new symbols, mathematical symbols, and every symbol is having a suffix. So, the suffix V, DSB and DPB, these are the suffixes for the two symbols. Okay, so let us, if we understand the meaning of every letter in that suffix, then it is easy to remember the meaning of the symbol. So let us go ahead. Right now we know that we want to find out these two values, and the least of those values is going to be our bolt value. Okay, so let us proceed like this. Single shear capacity of one bolt. What is VDSB? Capital VDSB. The meaning of this is D stands for design value. Then S for single shear and B for bolt. So first of all, we have to consider the bolt, how much the bolt can resist in shear. The bolt can resist in shear a value of VDSB. Now here we have to have a quick recap of the meaning of the words single shear and double shear. This we have already seen in the earlier video, that in a bolted connection, a bolt can break due to shear failure. This is one mode of failure of a bolt. Now that shear failure of a bolt can be either single shear or double shear type. The meaning of the term single shear, I will just repeat as a revision. The meaning of the word term single shear is that the bolt is cut at one cross section only in shear. Okay, there is shear failure of the bolt only at one cross section. When will this occur? When this type of single shear failure will occur? It will occur when you are having only two plates connected by one bolt. So here we are having plate 1 and plate 2, only two plates are connected by a single bolt or a bolt. Then that bolt will be failing in shear due to single shear. If we had three plates instead of two, we could have a bolt failing in double shear. So that is not the case in this problem. So first of all, we have to understand from the number of plates in the problem that whether your bolt will fail in single shear or double shear. So here the term single shear comes because we are having only two bolts. I mean only two plates connected by bolt. So single shear capacity of one bolt. So it is given by this formula. This formula requires to be remembered as it is. So it is 0.462 FUB NN ANB. So these are the symbols used in the formula. These are the terms. Now F stands for permissible stress or the stress material stress. FUB, it is the ultimate bolt stress, which we have already taken as 400. You can see here FUB is 400 from the grade. So I will put this 0.462 into 400 FUB. Then NN. NN means how many bolts we are right now talking about? So we are talking about a single bolt. You can see here single shear capacity of 1 bolt. So we are talking about only 1 bolt right now. So this Nn is number of bolts. So this is 1. Then A and B. A and B is the cross-sectional area of the bolt which is resisting this shear. You can look at this small diagram. At the bottom here the bolt has got cut. So the cross-sectional area at this thread is A and B, which we have calculated here. So this is 156.78. So this has been taken here. So this is the substitution of the numerical values in this formula, and we get the answer as 28973 Newton, which can be rewritten as 28.98 kilonewton. Since it is convenient to handle the numbers in kilonewton instead of Newton, we are taking it like this. Then bearing capacity of thinner plate. Bearing capacity of thinner plate is given by VDPB. VD, P for plate, B for the bearing, B for bearing. Now the formula is 2 kb d tp fu. Again, this second formula is also to be remembered as it is. To calculate the bolt value, you have to remember only two formulae like this. So this is the second formula you have to remember. In this, 2 is a constant. Then kb. What is this kb? Now this kb is a little tricky factor which the IS 800 is giving us. Now this kb is having the value which is least of, smallest of 4 values. You can see here factor kb. What is that factor kb? It is least of, or the smallest of 4 values. What are these 4 values? You can see here E upon 3d, P upon 3dh minus 0.25, FUB upon Fy and 1. So out of these 4 values, which is the smallest that we have to see, and that is the value of kb. Now it is very simple to calculate these values. This is the third formula you have to remember for these bolted connections. So E upon 3d. E is edge distance, here it is written. D is the diameter of the bolt itself, D, that is 16 mm. So here you can see, here the substitution has been done. E upon 3D, E is 30 upon 3 into D, 3 into 16. The second value is P minus 3DH. P pitch is 40 mm. You can see here pitch P is 40 mm upon 3 into 18. So 3DH. DH is 18, D is 16, minus 0.25. So this is the second value. Third value is FUB upon FU. So FUB is 400, you can see here, and FU is 410, and the last value is 1.0. So all these values, they calculated, when they are calculated, they amount to these values, least of 0.625, that is E upon 3D, 0.49, that is this second factor. Then the third is 0.97 FUB upon FU, and this is 1. So if you can see these 4 values, 0.625, 0.49, 0.97 and 1. Out of these 4 values, you will see that the lowest value is this 0.49. So we get the factor KB as 0.49. So you have to calculate this factor KB like this. So in this VDPB, we have got 2 into 0.49. Then what is TP? TP is the thickness of the plate. So this thickness of the plate is taken as 16. I mean, the thickness of the plate is 12 mm. D is diameter of plate, that is 16 mm. Diameter of bolt, that is 16 mm. This TP is the thickness of the plate. Now we have got 2 plates, one is 16 mm and the other is 12 mm thickness. So out of these 2 thicknesses, what to take? So you have to take the thinner, because we are finding out bearing capacity of thinner plate. So this is 12 mm into the last value is FU. This FU is the value 410 as seen here. So on substitution of these values, we get this final answer as 77.41 kilonewton. So with this, we get the two values. Hence the bolt value BV according to this formula is least of VDSB, that is 28.78 kilonewton, and the other 77.41. So this is the second value. So out of these two values, the smallest value is 28.98 kilonewton, which is actually the bolt value of this 16 mm bolt which we are talking about. So in conclusion, the answer of the step 1 is that the bolt, a single bolt can resist a force of 28.98 kilonewton, which we can say is the bolt value of a single bolt. Continuing the same problem, in the step 1 in the last step we calculated the BV bolt value as 28.98. Now we proceed for the second step. The second step is very short and very simple. Once we know that we have got a single bolt capacity as 28.98, we want to resist a total force of 105. So we can calculate what is the number of bolts that we will be required to provide. Now, so the number of bolts required to transfer the force N is the number of bolts equal to PU, that is the total ultimate force that is to be resisted, upon BV, what is the bolt, the shear or the force resisted by a single bolt. So this is 105 kilonewton upon 28.98 kilonewton. So this amounts to 3.62 bolts. Number of bolts equal to 3.62. Now it is obvious that it is impossible to provide 3.62 number of bolts. So it is to be rounded off to nearest bigger integer. So that is 4. So the conclusion is that we have to provide 4 bolts of 16 mm to resist an ultimate tensile load of 105 kilonewton, with the rate that every single bolt will resist this much of the force. Now the next question is whether you will provide all these 4 bolts in a single line, or will you provide the bolts in 2 lines, 2 in each, like that. All the options are available with us. Now usually we will try to provide the bolts in a single line, and that is what will be called as a single line bolted connection or single bolted connection. A single bolted connection does not mean that only one bolt is there in the connection. It only means that there is a single line. The bolts are provided in a single line. So this is the conclusion. Provide a single line bolted connection. So this is if you look at this diagram, here we see all the detailed distances and the dimensions of the bolted connection. Here you will see 4 bolts. All the 4 bolts are of 16 mm diameter. Then there are the pitch. The pitch is the distance between the bolts, that is 40 mm as we have calculated in the earlier slide. The edge distance E is 30 mm. This is also calculated from the earlier slide. Now this is the force. Now this is the top view. This is the sectional view. 4 bolts of 16 mm diameter at 40 mm center to center. These 4 bolts are shown here. So in this way we can say that, as a summary, that these 2 plates which are given in this problem statement, they are connected by 4 bolts of 4.6 grade 16 mm diameter in a single row with edge distance of 30 mm and pitch of 40 mm. So this is the conclusion of this problem. Friends, before we close this video, we will go through some probable variations in the same problem. The same problem can be asked with little variations. In that case, the total concept remains the same, the procedure also remains the same, but use of some numerical values will be little different. So the first variation is this, that ultimate load or factor load may be given directly instead of working load. In this problem, we know that working load of 70 kilonewton was given and we converted that into the factored or ultimate load. But this value may be directly given as take tensile ultimate load as something 105 kilonewton and so on. In that case, you don't have to do that calculation of TU from T. Then the second is the values of FUB and FYB may be directly given instead of the bolt grade. Here the bolt grade of 4.6 was given. Instead of that, we can be given directly the value of FUB and FYB. We calculated a value of FUB and FYB from the 4.686 grade of bolt. Then the third variation is calculation of only bolt value may be asked as a separate problem. In this case, in this problem, step 1 was calculation of bolt value and step 2 was design of connection, that is number of bolts and all the things. So step 1 only can be a separate problem, and in that case you don't have to go for step 2. So a big problem can be divided into small separate problems also. Then the fourth variation is this, that number of bolt lines or bolt rows may be mentioned in the problem statement. If you look at this problem statement, they have not said about what is the number of bolt lines. You provide 2 bolt lines or 1 bolt line or anything like that. So you had a choice of deciding whether you should have 1 or 2 bolt lines. But in some problems, they may give the statement like this, for example, design a double bolted connection. If they mention it as double bolted connection, it will mean that they are expecting the bolts to be provided in 2 rows. Double stands for 2 rows. So whatever number of bolts 4 you have come out with, then those 4 bolts will be provided in 2 rows of 2 each instead of 4 bolts of 1 row each. So that is the fourth type of variation that can come in the same problem. The fifth variation is this, that the load may not be given directly. The value of load itself, ultimate load or working load, nothing will be mentioned in the problem about the load. So if load is not mentioned, how will you calculate the number of bolts and design the connection? If the value of bolt is not explicitly or directly given, you will have to calculate the value of maximum possible load the plate can take. So in that case, you will have to calculate the value of T also as Fy into area of plate. Fy is the yield stress of the plate. We are expecting that the plate will take the load up to yield point, and area of the plate, cross-sectional area of the plate. Now there are two areas, 100 by 16 and 80 by 12. So you'll have to take the smaller value of area, that is 80 mm by 12 mm, that means will be area of plate into Fy. So this value of T will have to be taken, and then we will be able to solve the problem. So these were some 5 variations that are possible in the same problem. If you can refer to different problems and solve about 5 problems of the similar type, so that you can master this design of a bolted connection with lap joint. Now we come for a self-test for formative evaluation. So pause the video and write on a paper the answers of the following questions. The first question is define bolt value. This is a remembering type question. Second is calculate safe ultimate load a bolted connection of single row, 6 bolts, 20 mm diameter in a single line, transfer safely. So this is a second question, and this is an application level question. So you are supposed to solve this second question also. If you have given enough time for solution of the questions, then you can continue with this video. So coming to the end of the video, let us sum up whatever we studied in this video. We started with the expectation that The learning outcome will be design of a bolted connection for lap joint. Now you have to check whether you are able to design a bolted connection for a lap joint. Then we use some key terms in this video. So these are the key terms: single bolted and double bolted lap joint, bolt value, shear capacity of bolt, bearing capacity of bolt, bearing capacity of plate, working load, ultimate or factored load, and bolt line or bolt rule. So these are the key terms. The key terms will help you to hold the content of the entire video in your mind properly. So contact your teacher for any doubts or queries you may face while understanding this video. Then a summative assessment quiz will be provided in the form of a Google quiz as usual. So attempt the online summative assessment quiz provided by the teacher. With this, we come to the end of this video. I hope you enjoyed the video. Thanks and goodbye till the next video.